In this part of the chapter, we're going to primarily focus on acids and bases. So some of this will be a review from General Chemistry 2, and then we'll take some of those concepts that you've previously learned about acids and bases and apply them to organic molecules. You may recall that there are three major acid-base theories. Arrhenius acids talks about what's an acid or what's a base when you're specifically dealing with the solvent of water. We'll look at the Bronsted-Lowry theory, which talks about protons being donated or accepted in a little bit. That's going to be the one that we spend most of our time on. And then later we'll talk about Lewis acid-base theory, which is the most broadest definition of what an acid or a base could be, and it will make more things be able to be considered an acid or a base that we might not normally expect them to be. So Lewis acids and bases deal with electrons. So Arrhenius is the most restrictive of what can be an acid base. Bronsted-Lowry is kind of in the middle, and then Lewis opens it up to a lot of things. Bronsted-Lowry acids and bases are very important when studying organic reactions. A Bronsted-Lowry acid is something that can donate a proton, so we call it a proton donor. Whereas a Bronsted-Lowry base is something that can accept a proton, so we call it a proton acceptor. There are certain things that a base must have in order for it to accept a proton, and if something's going to be an acid, it at least has to have one proton that it can donate. You might also recall the concept of conjugate acid-base pairs when looking at an acid-base equilibrium. So in this basic example, we have a strong mineral acid. Something like hydrochloric acid, which is HCl, is a much stronger acid than any organic acid we're going to be dealing with. But it's a good example because we can see that there's a hydrogen on HCl that can easily be donated to a base. So the hydrochloric acid will act as our Bronsted-Lowry acid or proton donor. If it's in water, it'll be a proton acceptor because the oxygen of the water has two lone pairs of electrons that can donate their electrons essentially to the hydrogen of the acid. And so they can accept that proton. So what will happen is the electrons will react with the acid of hydrochloric acid and grab that proton from HCl. The electrons that are in between the hydrogen and the chlorine, that covalent bond there, those electrons end up getting left with the chloride. So it becomes the chloride ion because it picks up those extra electrons within that covalent bond. When the base grabs the proton, it's grabbing a proton, which is a hydrogen ion. It doesn't take the electrons with it. So those electrons usually stay with the other part of the acid. So now our base, which was water, has picked up that extra proton to form H3O+, which is the hydronium ion. Notice the oxygen in the hydronium ion is actually the atom that is bearing the positive formal charge. Normally we just said H3O+, that molecule has a +1 charge overall. Well, it does, but now that we've studied more in depth what atoms have, what formal charge, and what that really means in terms of resonance, we can see that it's the oxygen that has the formal charge of +1 in this hydronium ion. The chloride comes from those lone pair of electrons that were left from that covalent bond when water abstracted that proton. So now the formal charge on the chlorine is -1 because it likes to have 7 valence electrons. It's group 7A. It has 8 around it, so it has 1 extra, -1. That would be called the conjugate base. So here we have our first pair. We have our hydrochloric acid and the chloride ion. That's one conjugate acid-base pair. They differ by 1 proton. The conjugate acid will be our hydronium ion. That's the conjugate acid of water. So the other pair that differ by 1 proton is this conjugate acid-base pair. So you should be able to predict what the products would be from a given acid-base equilibrium using Bronsted theory, and then also be able to identify conjugate acid-base pairs. This is something we would have covered in depth in Chemistry 112. In this example, we're being told what species is acting as the acid and what species is acting as the base. If we were not told that, we would have to figure that out for ourselves. But for now, let's just practice on reviewing drawing the products from an acid-base reaction. So we have an amine, we have a nitrogen with two methyl groups and a hydrogen coming off. So this would be an example of a secondary amine using our functional group naming. And it's reacting with water. If water is functioning as the acid, then this proton is going to be abstracted by the base. So what will happen is the lone pair of electrons on the nitrogen will grab that proton. The electrons in the covalent bond between oxygen and hydrogen will stay with the oxygen. So a base is a proton acceptor, an acid is a proton donor. Our products then are going to be, we're going to have our nitrogen with our two methyl groups, and now we have another hydrogen on there, the one that we took from the water. Our nitrogen is going to have a positive 1 mole charge now. Our other product is going to be OH. We're left with water with one hydrogen bond to it. It had two lone pairs of electrons. Now it has three because that covalent bond became another lone pair of electrons on the oxygen. And so our oxygen now has a negative 1 mole charge. So when we're looking at our pairs here, our secondary amine and our ammonium derivative is going to be one conjugate acid-base pair. This would be the conjugate acid of our base. And then our other one is our water and hydroxide, which is OH minus, would be the conjugate base for our acid, which was water there. So those are our two conjugate acid-base pairs. Now, right below this one, we've just flipped it around. We've said, how will this change if our acid is the secondary amine and our base is water? So if our base is water, that means that our base is going to abstract a proton from our acid. And this is going to have to be the proton that it grabs. That's the only one that's on the secondary amine. So our electrons on our water will grab that proton from the amine. The electrons in the covalent bond get left with the nitrogen. And our products here then will be when our water picks up another proton, and this should look familiar to you. We have one lone pair of electrons left over. This could be, for example, the proton that we grabbed off of our amine. And now our oxygen has a +1 formal charge. So this would be the conjugate acid of our water when it's base. So hydronium ion is our conjugate acid. And then our other product is going to be our secondary amine when it loses its proton. So we still have the two methyl groups. We had one lone pair of electrons. Now we have another lone pair of electrons. So that nitrogen will have a -1 formal charge. And then this would represent the conjugate base of our secondary amine when it's an acid. So those are our two pairs in this case. Remember that a conjugate acid-base pair is two species that differ by one proton. And we're using our curvy arrow notation again too that we just learned about in resonance. These curvy arrows are not just used in resonance structures. Curvy arrows are used for mechanisms, for showing reactions, for showing resonance structures. Every time you see these curvy arrows, remember that that means the movement of two electrons. The tail end is where the electrons are starting, and where it points to is where they are ending. So we're trying to indicate that by showing the flow of electrons. Sorry, that last slide skipped ahead a little fast. The bottom question said, what do you call a substance that can act as an acid or a base? We had a special name for that type of substance, and it was called amphoteric. So in that last example, the secondary amine was amphoteric because we saw it could function as an acid or a base, and water was also amphoteric. There are a lot of substances that have a lone pair of electrons that will allow them to accept a proton and be a base, and they'll also have a proton on them where they could donate it and act as an acid. Whether they actually act as an acid or a base in a reaction in real life will depend upon who they are reacting with. And we'll kind of review that, how you determine if it's going to be an acid or a base in a little bit. So coming back to the curved arrows we were talking about, we use that arrow to show the movement of electrons. And right now we're focusing on pairs of electrons moving together. So that means 2 electrons. When we look at an acid-base reaction, this is just a very generic Bronsted-Lowry acid-base reaction. You're going to have usually some base. It could be neutral, but usually you might see that your base has a negative formal charge because it has extra electrons around it. And what will happen is you'll use a curvy arrow to start at the base, so starting where those electrons are, heading towards the proton of the acid. You end at that proton because that's what your base is grabbing. And then, as we saw, the electrons in that covalent bond between the proton of the acid and whatever else it's bonded to, here we're just generically saying it's bonded to A, that bond has to break because the base is just grabbing the proton. So the 2 electrons in that covalent bond go to the other part of the acid, so A in this case. And then you'll have a new bond formed between your base and your proton in your products. And then you'll be left with A minus because there's going to be a negative charge usually on whatever was left over from the acid because it picked up those extra electrons in that covalent bond. So that's why this is just a really generic acid-base reaction template, but you can use it for a lot of real-life acid-base reactions as well. So when we're looking at these curved arrows, the only way we can really say that they are different from the ones we were using before for resonance is that now we're actually using them in a reaction. Whereas when we were drawing them in resonance, we were just delocalizing those electrons. We were moving the electrons around the structure, but we weren't going from reactants to products when we were drawing resonance structures. Also keep in mind that when we draw resonance structures, we also use these arrows, which are the resonance arrows. Those are the double-headed arrows that you have to put in between resonance structures. You still use curvy arrows to show electron delocalization, but the resonance arrows indicate that you are drawing resonance structures. So now we're using curvy arrows to actually show a reaction. We're going from reactants to products. And later we'll expand upon this and build a full reaction mechanism, which it's really no different than this acid-base one here, except for this one is occurring in essentially one step. A mechanism is often, 2 steps, 3 steps, 4 steps. It could be a lot of steps to get from reactants to products. But if you understand using curvy arrows, you can understand drawing a reaction mechanism. Something else that we're going to review from general chemistry is how we determine if an acid is a weak acid or a strong acid, or how we determine if a base is a weak base or a strong base. We want to be able to quantify acidity and say if something is stronger or weaker than something else. This is going to be helpful in predicting the direction and the progress of reactions, meaning how far to the left or how far to the right will the equilibrium lie. We can talk about quantitative strength analysis. This is where we're using numerical values. That's why it's called quantitative. Notice the N right here, in order to analyze acid or base strength. You might recall from general chemistry, we talked about Kas and we talked about K sub Bs. Ka was the acid dissociation constant and Kb is the base dissociation constant. Usually in organic chemistry, we use pKa values or sometimes pKb values to actually talk about the strength of an acid or base, where you can calculate the pKa by taking the negative log of the Ka, just like you would calculate the pH of something. We'll also learn how to look at a structure and do a qualitative analysis of strength. So qualitative isn't using numbers, but we look at the structure and we analyze different things about it to compare the stability of it to other acids or bases, and then we can say who is stronger or weaker based upon how stable or not stable a given structure is. So let's look at a quick general chemistry review of Kas and pKas. Ka is the acid dissociation constant, which is an equilibrium constant for the reaction between an acid and water. That's what's assumed is the solvent when you're looking at the Ka. So if we have some generic acid, which we're going to call HA, and this would be a weak acid, usually HX is used to represent a strong acid. We only write equilibrium dissociations for weak acids. Remember that strong acids dissociate completely. So for a strong acid, HX, that would fully break up into a proton and its conjugate base. We would not write an equilibrium for that, which is why we used a single arrow. So when HA reacts with water, you form A- and hydronium ion because water would be the base, and then HA would be the weak acid, so the base would pick up that proton from the acid. We then could say that Ka is equal to the concentration of the products, hydronium times A-, over the concentration of the reactants. Remember that we left water out of the equilibrium expression because it was a pure liquid. Pure liquids and pure solids did not get included in the equilibrium expression because their concentrations were essentially constant. So once we wrote that and we figured out the Ka value, or we looked at a chart to know the Ka value, we could say how strong or how weak an acid was when comparing it to something else. So how will the magnitude of Ka essentially affect if it's going to be a weak acid or a strong acid? And what we learned is that as Ka increases, acid strength increases. And that meant when we looked at our chart that we had, the acids that were at the top of the chart had a very large Ka. In fact, some of them were so strong that they didn't even give you a numerical value. And as we worked our way down, the value for the equilibrium constant, the Ka, got smaller and smaller and smaller, and the acids got weaker and weaker and weaker. So you can directly look at the magnitude of Ka to know how strong an acid is. You could see that given Ka values have a very large range because we have really, really strong acids and we have really, really weak acids. So they could range from 10 to the negative 50th all the way to 10 to the 10th. But usually we use pKa because it's quicker and shorter. So when we want to calculate the pKa, we would take the negative log of the Ka. And since we're taking the negative log of it, that creates this inverse relationship between Ka and pKa. A high Ka is equal to a low pKa, and that would make a strong acid. Sometimes pKa values are even negative numbers, and those are really, really strong mineral acids such as sulfuric acid or hydrochloric acid, for example. So strong acids have low pKa values. There's this inverse relationship between them, just like you would have seen for the concentration of hydronium and the pH. As hydronium ion concentration increased, the pH decreased. A lower pH indicated a stronger acid. So that's another way that we have learned about acid strength, is looking at pH as well. On the right, we have a chart of various pKa values for a given hydrogen acting as an acid. So that hydrogen highlighted in red on all of these structures is the hydrogen that would be donated if that molecule is acting as an acid, according to Bronsted-Lowry theory. So each pKa unit that you see represents an order of magnitude or power of 10. So when we want to actually quantitatively talk about how much stronger one acid is than another, we have to think about the difference between those numbers as a given power of 10. So for example, how much stronger is HCl or H2SO4, and by how much? So H2SO4 is sulfuric acid, and that's at the top of our chart. It has a pKa of -9. If you go down to HCl or hydrochloric acid, has a pKa of -7. So we just said that the lower the pKa value is, the stronger the acid. So H2SO4 is stronger than HCl. Hydrochloric acid is a little weaker than sulfuric acid, but by how much? We can actually use the pKa values to say how much stronger one is than the other. So if we look at the difference between those two numbers, 9 minus 7, that has a difference of 2 pKa units. But what that really means is 10 to the 2 would be 100. So sulfuric acid is 100 times stronger than hydrochloric acid. You also might recall from our acid-base chart that when you're looking at the acid side, it goes from strongest to weakest as you go from top to bottom. But there's an inverse relationship between an acid and its conjugate base. If the strongest acid is at the top, then the weakest base is at the top when we're looking at its conjugate. And if the weakest acid is at the bottom, then the strongest base would be present at the bottom when we're looking at that acid's conjugate base. So there's an inverse relationship between them. We can use pKa values, that means then, to also compare the strengths of a given base. So, for example, we said that sulfuric acid had a pKa of -9. If we were to compare that with HCl, which had a pKa of -7, that means that our conjugate base for HCl, which it's cut off a little bit, that's the chloride ion, and our conjugate base for sulfuric acid is HSO4-. We know that our chloride ion is going to be a stronger base than our conjugate base for sulfuric acid. Because we know the strength of those acids, we can compare them. We can also compare the strength of the conjugate bases. So the general rule of thumb is that the stronger an acid is, the weaker its conjugate base will be. And that has to do with the fact that for a really strong acid, it really wants to give up that proton a lot. It wants something to take that proton. The conjugate base that is the result of losing that proton is very stable. So if it's very stable, that means that it doesn't want to go back and react. So it's going to be a weak base because it doesn't want to pick up another proton. This oxygen does not want to react with something else and grab a proton and go backwards to forming its acid structure. So that's what makes it weak, is that it's very stable. On the other hand, if you have a weak acid and that lost a proton, and you formed something like this where you have a carb anion, a negative charge on that carbon, this is a strong base because it's not stable. That really badly wants to react with almost any proton it can find and go back and form its acid structure. So the strong bases are unstable and the weak bases are very stable. The same can also be said about the structures for acids as well. But there's this inverse relationship between acid strength and conjugate base strength that you're going to want to be familiar with. You also might recall that we can use Ka values, or now pKa values, to analyze the direction that a reaction will go. Will it go left or will it go right? And then we used a longer arrow pointing in the direction to show what way it will favor. So when we look at this acid-base reaction, we have a base. This generically is called an alkoxide ion. It's an organic molecule that has an oxygen with a negative charge. The real name of this would be tert butoxide. Alkoxide is just generic, any alkyl group, but because this is a tert butyl group on there, that's where the name tert butoxide would come from. And that's a base. We have an oxygen that can grab a proton from water, which is our acid. So our curvy arrows would be starting with our oxygen, going to grab that proton from water. These electrons in this covalent bond will stay with that oxygen. So we needed two curvy arrows there. Our conjugate acid that we form when our tert butoxide picks up a proton is an alcohol functional group. And our conjugate base of water is the hydroxide ion. So this would be one conjugate acid-base pair, and this would be another conjugate acid-base pair. So we were given some pKa's here. If not, we could look them up for the two acids. You either want to compare the two acids to one another, or you want to compare the two bases to one another, never an acid and a base. So notice our acid, water, has a pKa of 15.7, and our alcohol as an acid has a pKa of 18. So since the acid for water, the pKa is lower, that means it's our stronger acid. And our conjugate acid alcohol has the higher pKa, so that means it's our weaker acid when comparing the two. We also now could say something about the bases. Once you know what side is stronger or weaker for the acid, the same will be true for the bases. The conjugate base of hydroxide has to be the weaker base. They have to be on the same side, the acid and the base, the weaker pair. And our tert butoxide ion must be our stronger base, just because those also have to be on the same side, the stronger acid-base pair. So what will happen is the reaction will favor the weaker acid-base side. So what we learned is that we drew the arrow longer in the direction of the weaker pairs, because the stronger ones are stronger, which makes them more apt to react with one another. And so the products are going to be favored in this case, and our arrow, our equilibrium arrow pointing longer in the direction of our weaker ones means that at equilibrium we have a larger amount of those two. And because they're weaker, they're not going to want to go back and form a lot of the stronger ones. So that's why this arrow down here is much smaller. So we drew the arrow longer in the direction pointing towards the weaker acid-base pair because that was our favored direction. Let's use these pKa values to analyze what side of this acid-base equilibrium is going to be favored. So here's just another example. We have a base, which this base is going to be a carbon with a negative charge. So this is a carb anion, and it's derived from butane. And what's going to happen is that base is going to grab a proton from our acid, which in this case our acid is water. Our pKa for our acid is 15.7. And remember, these electrons within this covalent bond right here stay with the oxygen when using our curvy arrows. Our conjugate acid then is going to have picked up that proton from water. So there's now essentially butane that we formed. We don't have that carb anion anymore. Really, we're just honing in on that one hydrogen there, but there still is two hydrogens here, two hydrogens here. This would be a CH3 group at the end with 3 hydrogens, and there are still 2 other hydrogens there. They're just not being shown in the line bond structure because we're just focusing on the hydrogen that was picked up from the acid. Notice the pKa of something like butane, a proton on there. It has a pKa of 50. It is significantly less acidic than our water is. Our water is the stronger acid. This butane is the weaker acid, much, much weaker. And then what we're left with is the conjugate base for water, which is our hydroxide ion. We have our conjugate acid-base pairs, so water paired up with hydroxide, and our carb anion with our butane. In this case, notice that a single arrow was drawn. We could, say that this was an equilibrium to some extent, and if it was, it would be pointing towards our weaker acid and weaker base. Also, hydroxide would be the weaker base on the same side as the weaker acid, and the carb anion would be our stronger base, same side as the strong acid. Those two always go together. So it would point to the right. But notice that we're not even using a double arrow here because this really isn't